Right now, like all across the globe, this whole race to build better artificial intelligence is, well, it's fundamentally breaking the physical power grid.
Oh, absolutely. It's straining everything.
Right. I mean, if you were to take the newest, most advanced AI chips off the assembly line today, put them in a standard data center rack, and try to cool them with, traditional spinning fans, they would literally cook themselves alive in just a matter of seconds.
Yeah, they just melt down.
Exactly. We've reached this wild point where the software we're writing is simply too powerful for the physical world to handle without a massive shift in engineering. So welcome to the deep dive. Today we're taking you on a journey to the absolute bleeding edge of artificial intelligence infrastructure.
And it's a conversation that completely upends how we normally think about software. We're so conditioned to view AI as this ethereal mathematical concept that just sort of lives up in the cloud.
Yeah, the magical cloud.
Right, but the reality is that the cloud is incredibly heavy. It is burning hot, and it requires industrial-scale plumbing just to survive. We are essentially looking at the physical constraints of our digital future.
And to figure out exactly how the industry is trying to stop these servers from melting down and, stop the power grid from collapsing along with them, we're pulling from a very specific, kind of rare set of sources today.
Very rare, yeah. These aren't your typical PR releases.
No, not at all. We have a series of internal product management presentations and these really deeply technical system walkthroughs. They were recorded throughout 2025 by Kevin Kulp, who is the product management head of cloud management solutions over at Supermicro.
Which is what makes this material so incredibly valuable for us to look at. You aren't getting the shiny marketing brochure here.
Definitely not.
These sources are the deep, in-the-weeds technical validations of their SuperCloud Composer software. We're getting a front-row seat to how the hardware industry is frantically building the tools to manage the absolute latest Nvidia AI rack architectures.
Okay, let's unpack this. Because the inciting incident for this entire wave of hardware innovation isn't just a desire to make things look cooler, right? It's a literal crisis. And the sources make this abundantly clear right out of the gate.
They really do, and they use a very specific word to describe these modern accelerated servers. They call them thirsty.
Thirsty. That's such a visceral way to put it.
It is, but it's accurate. The blunt reality presented in these walkthroughs is that there are simply not enough power resources within the existing electrical grid to drive the AI models we're currently trying to build.
Wow. Just not enough juice.
Exactly. When you're training a massive large language model, you're pushing millions of complex math operations through these specialized chips every fraction of a second. That computation takes immense electricity.
And all that consumed electricity instantly turns into heat, right?
100%. It's basic physics.
And we aren't talking about the kind of heat that, makes your laptop warm your legs on the couch. We're talking about industrial smelting level thermal output packed into a space the size of a few pizza boxes.
Yeah, it's hard to even conceptualize the density of that heat.
Which leads directly to the major industry shift that Supermicro and Kevin Kulp highlight. Supermicro, alongside the absolute titans of the semiconductor world, so companies like Intel, AMD, and Nvidia, they've all publicly declared a mandate.
A huge mandate.
Right. Moving forward, any high-end accelerated server will strictly require liquid-cooled solutions. Air cooling. Yeah, the loud blowing fans we've associated with computers for half a century is officially dead for high-end AI.
It's totally dead. And the reason is that the physics of air simply can't keep up anymore. I mean, air is actually a terrible conductor of heat.
Is it? I guess I never really thought about it.
Oh, yeah. For decades, traditional data centers basically operated by acting like massive, highly inefficient refrigerators. They would pump millions of cubic feet of freezing cold air down these aisles. The servers would suck it in, pull some heat off the chips, and just blast it out the back.
Like a giant window AC unit.
Exactly. But the thermal density of the new AI chips, specifically the Nvidia Blackwell platforms like the GB200 we're looking at today, has just skyrocketed. You physically cannot push enough air across that surface area fast enough to remove the heat. It hits a thermodynamic wall.
So the air just isn't dense enough to grab the heat and take it away.
Right. But water, on the other hand, is significantly denser. It has a much higher specific heat capacity, which means it can absorb and carry away massive amounts of thermal energy exponentially faster than air.
I hear that, but I want to push back on this just a little bit.
Sure.
Because whenever I see massive hardware requirements suddenly spike like this, my first thought is usually about lazy coding. I mean, is liquid cooling just an expensive, elaborate Band-Aid for incredibly inefficient software?
That's an interesting point.
Like, are we just writing bloated code and
Yeah.
trying to solve our bad math with advanced plumbing? Or is this a fundamental limit of physics?
Well, it's a very fair question to ask, but in this specific scenario, we are absolutely hitting a wall of atomic physics, not just software inefficiency.
Really? So it's not just sloppy code?
No, not at all. To achieve the kind of parallel processing that a neural network requires, hardware engineers have spent the last decade shrinking transistors down to microscopic, almost atomic scales. They're packing billions of them onto a single piece of silicon.
Right. The chips are getting unbelievably dense.
And when you fire electrons through billions of microscopic gates all at once, the energy density per square inch starts to resemble a nuclear reactor core more than a traditional circuit board.
Oh, wow. So even if the software was mathematically perfect and completely optimized, the physical footprint of the chip doing the work is still going to generate that catastrophic heat.
Precisely. And this ties into a crucial concept mentioned in the presentation's PUE, or power usage effectiveness. This is essentially the gold standard metric data centers use to determine how much power they are wasting.
Okay, so how does that math work? What's a good PUE?
Well, a PUE of 1.0 would mean absolute perfection. It means 100% of the electricity coming from the power plant is going directly into the computer chips to perform calculations.
Zero waste.
Right. But traditional air-cooled data centers often run at a PUE of 1.5 or even higher.
Which means, wait, so for every megawatt of power the computers use to do actual math, another half a megawatt is completely wasted just running massive air conditioning compressor units on the roof to keep the room cold.
Exactly. It's wildly inefficient. And when you're building an AI factory in a region where the local municipal power grid is already stretched to its absolute breaking point, you cannot afford to waste a single watt on AC units.
Yeah, you can't exactly ask the local city to go build a new power plant just to run your cooling fans.
No, you can't. So moving to direct-to-chip liquid cooling, where chilled fluid is pumped directly over the hot silicon via these tiny microchannels, it captures the heat right at the source. It drives that PUE metric down dramatically closer to 1.0.
It makes total sense.
Yeah, AI is literally forcing data centers to evolve from traditional IT server rooms into these highly volatile, liquid-managed thermal facilities.
And the sources really hammer home the stakes of managing these volatile facilities. They use this fantastic car dashboard analogy that I think perfectly illustrates the risk here.
Oh, I love that analogy.
Right. Kevin Kulp argues that running a modern AI model without hyper-precise measurement tools is like hopping into a car to drive cross-country without a dashboard. No speedometer, no gas gauge, nothing.
It sets the stakes perfectly. Think about what goes into training a modern AI model. You aren't just running a quick script that finishes in 5 minutes.
No, it's a massive undertaking.
Right. These models can take 3, 4, or even 6 months of continuous, uninterrupted computation to finish training.
So if you're 2 months into a 3-month training run and you're flying blind without any telemetry, no temperature gauges, no fluid pressure alerts, and a single cooling node gets clogged and fails, that chip melts down.
And because these systems are so deeply interconnected, that single failure can corrupt the entire training batch.
That is terrifying. You just lost 2 months of compute time, which translates to millions of dollars in electricity and lost opportunity. So the dashboard isn't just a nice-to-have feature. It is the only thing preventing a multi-million-dollar disaster.
Exactly. And that profound risk is exactly what is driving a massive philosophical shift in how we physically design and manage the server racks themselves.
Because the stakes are so high, we just can't afford the old way of doing things anymore. We can't have bespoke, custom-built, haphazardly cabled server racks.
No, absolutely not. Which brings us to the physical embodiment of this new era. The sources dedicate a massive amount of time to breaking down the architecture of what they call the supercluster AI rack, specifically the Nvidia NVL72 platform.
And to understand why this specific rack is so revolutionary, we first have to understand how DevOps engineers used to do their jobs, right?
Right. The presentations contrast their new management software, SuperCloud Composer, or SEC, with their older generation tool called PodView. In the old days, a network admin would plug in a bunch of servers, boot up the discovery software, and the software would essentially crawl the network looking for independent devices.
Like it's just pinging things one by one.
Exactly. It would find a server here, a network switch over there, a storage drive somewhere else.
I always picture that old method like having a giant bucket of random Lego bricks just dumped on the floor. You know you have all the pieces, but they aren't connected into anything meaningful yet.
That's a perfect way to visualize it.
The human administrator would have to sit there, look at a virtual representation of an empty rack on their screen, and manually assign each of those discovered Lego bricks into a specific slot to build the virtual rack.
It was incredibly tedious, manual, and highly prone to human error. But what's fascinating here is the paradigm shift with the NVL72 architecture inside the SuperCloud Composer software. You no longer discover individual components.
Right.
The software discovers the entire 48U rack as one single combined entity.
It's treating this massive, heavy metal structure not as a collection of independent computers, but as a single living organism.
That is the exact philosophical leap. The entire 48 rack unit tall tower is the computer. And because it's treated as a single organism by the software, its physical anatomy has to be identical every single time it is built.
So Supermicro enforces an incredibly strict hierarchy. They break the rack down into 5 highly specific quadrants.
Walk me through this anatomy. I'm looking at the diagrams from the presentation, and it's a very dense tower of equipment.
Yeah, let's break it down from the absolute top of the rack down to the floor. What exactly are we looking at?
Well, at the very peak of the rack, the top quadrant, you have the management network grouping. This consists of 2 specialized network switches that are entirely reserved for what we call the BMC, the Baseboard Management Controller, and the SEC management metadata.
Now, for anyone listening who hasn't spent time freezing in a data center, what is a BMC, and why does it need 2 dedicated switches at the very top of the rack?
So a BMC is essentially a tiny independent computer built directly into the motherboard of a larger server. Its only job is to monitor the physical health of that server, things like temperature, voltage, and fan speeds.
Just a little health monitor.
Right. By dedicating 2 network switches entirely to this health data, Supermicro is guaranteeing what we call out-of-band management.
Okay, out-of-band management. I've always thought of that like the red emergency telephone sitting on the president's desk.
That's a great way to visualize it. If the primary data network, the in-band network, gets completely clogged because the AI is transferring terabytes of training data, or, if the main network crashes entirely, the system administrator still has that red emergency phone line.
Well, it can always get through.
Exactly. The out-of-band network allows them to dial directly into the hardware's nervous system, check the temperatures, and issue a hard reboot without ever touching the primary data traffic.
So the brain might be having a full-blown seizure, but the nervous system has a dedicated line to call for help.
I love that. Okay, so moving down from those top management switches, the diagram shows the first of 2 power shelves.
Yes, manufactured by Light-On Technology. This rack pulls so much electricity from the facility that it requires massive dedicated power distribution units just to funnel and condition that electricity safely down to the components below it.
Which feeds the third quadrant, and this is where the actual magic happens, right? This is the first compute tray grouping. The sources detailed that this section holds 10 individual compute nodes. And the hardware packed into just these 10 nodes is staggering.
It really is. They mentioned each compute tray uses 2 Grace ARM processors and 4 Nvidia Blackwell GPUs. Can you unpack those specs a bit? What does that actually mean for performance?
It means an almost incomprehensible level of compute density. To break it down, a GPU, or graphics processing unit, is the absolute workhorse of AI. NVIDIA's Blackwell GPUs are designed to do thousands of math problems simultaneously, which is exactly what neural networks need.
Right, they just chew through the math.
But those GPUs need to be fed data constantly to keep them busy. That is where the Grace ARM processors come in. ARM is a specific architecture of processor designed to be incredibly efficient at moving data around.
So they're like a logistics team.
Exactly. So in just one of these 10 trays, you have 2 highly efficient traffic cops, the ARM processors doing nothing but feeding massive chunks of data into 4 incredibly powerful math engines, the GPUs.
And there are 10 of those trays stacked on top of each other. But they all need to talk to each other to solve a single massive AI problem, which explains the 4th quadrant sitting right below them, the switch tray.
This is the critical bottleneck for any supercomputer. You can have all the GPUs in the world, but if they have to wait for data to travel over a slow network cable, they're just sitting idle, basically wasting power. So Supermicro places the compute interconnect tray right in the middle of the rack.
And it features 9 specific NVLink switches, right? Why NVLink specifically, and why exactly 9 of them?
So NVLink is a proprietary technology developed by Nvidia. Traditional network cables, like the Ethernet cable plugged into your home router, they translate data into packets, send them, and unpack them. That translation takes precious milliseconds.
It's too slow for this kind of work.
Way too slow. NVLink bypasses that completely. It allows multiple GPUs to essentially share the same pool of memory, reading and writing to each other at a hardware level. It is blisteringly fast. And they use exactly 9 of these massive switches because they have to route thousands of individual data lanes between the 10 compute trays above them and the final 8 compute trays sitting right below them.
So the physical location of those switches in the exact center of the rack isn't an accident. They're actively trying to kick the physical copper cables connecting the top servers and the bottom servers as short as physically possible. Because at these speeds, the actual time it takes an electron to travel down an extra foot of cable introduces latency.
Exactly. Every single millimeter matters when you're trying to make 72 GPUs act like one single processor. So beneath those switches, you have your remaining 8 compute trays, followed by the second light-on power shelf to feed the bottom half of the rack.
And finally, sitting at the absolute base of this massive metal tower, we have the anchor, the component that makes this entire liquid-cooled reality possible, the CDU, or cooling distribution unit.
Which we're going to explore the mechanics of in depth shortly, but it always resides in Rack Slot Unit 1, right against the floor.
So looking at this entire 5-quadrant layout, management, power, computes, switches, computes, power, CDU, it is so rigidly defined. If I'm a massive tech company spending millions of dollars on these racks, I usually want to customize my hardware. I might want 12 compute nodes on top, or I might want a totally different brand of network switch. Why does Supermicro strictly enforce this exact non-negotiable hierarchy every single time?
Because in the world of hyperscale AI, customization is actually the enemy of progress.
Really? How so?
Customization requires bespoke engineering. Supermicro's philosophy here is to create a perfect plug-and-play building block. By enforcing a streamlined, identical layout, they drastically simplify the cable plant configurations.
Right. If you're a facility manager trying to stand up a new data center with 500 of these racks, you really don't want your technician standing on the floor for 3 weeks trying to read a custom wiring diagram for every single individual rack.
Exactly. You want them rolling the rack in, plugging in the main power, hooking up the facility water lines to the CDU, and just turning it on. Furthermore, this strict standardization is the only reason the SuperCloud Composer software works so seamlessly.
Because it knows exactly what to expect.
Yes, the software doesn't have to guess where the network switches are. It knows with absolute mathematical certainty that they are always in that exact middle quadrant. It allows the management software to scale infinitely without ever getting confused.
That perfectly transitions us to the human element of this equation. We have this 48U liquid-filled, heavily powered organism. But how does a human being actually drive this thing? If you were a DevOps engineer sitting in a control room, how do you interact with an architecture this dense without just drowning in a sea of raw data?
That is the core challenge that the SuperCloud Composer, or SEC software, is trying to solve. The source has spent a significant amount of time walking us through the SEC user interface, specifically looking at the February Y25 release and their move into the version 3.11 environment.
And before you even see a single piece of data, the system forces you through an incredibly strict access and security gateway.
Which totally makes sense. If this rack represents millions of dollars of hardware and potentially billions of dollars in intellectual property training on it, you can't have a junior developer accidentally turning off the power switch.
Right. The stakes are way too high. The sources outline a deeply layered security approach for this.
They do. For day-to-day enterprise use, the software integrates with major identity providers. You can use protocols like Keycloak for single sign-on, meaning an engineer uses their secure corporate credential to gain access.
Very standard for big tech.
Yeah, and it natively supports Microsoft Active Directory, too, seamlessly handling both single and multi-domain environments, which is crucial for massive global corporations that might have different engineering teams across different continents.
But what happens if the corporate network goes down? Like, what if the Active Directory server crashes and nobody can log in, but the AI rack is currently overheating and needs immediate intervention?
That is where the failsafe comes in. The SEC architecture includes a globally protected admin account with local access credentials that are hard-coded into the SEC's secure kernel appliance itself.
It's the digital equivalent of breaking the glass to pull the fire alarm.
Exactly. Even if the entire corporate IT infrastructure collapses, a super user with physical or direct local network access can bypass the broken directory servers, log directly into the kernel appliance, and take control of the AI supercluster to prevent physical damage.
So Assuming the network is healthy and you log in through standard channels, you land on the main SEC dashboard. But the sources are very quick to point out that this initial landing page is almost entirely read-only for general users.
Right, you get a high-level 30,000-foot view of your data center's health, but you can't actually touch anything or break anything.
To do the real work, an authorized admin has to navigate to a specific new module on the left-hand menu, aptly named the AI supercluster module.
Yeah.
And the moment you click into this, the software's philosophy of treating the rack as a single organism becomes entirely visual.
It really does. The UI shifts away from traditional spreadsheets. You aren't looking at endless rows of IP addresses and MSC addresses anymore.
Thank goodness.
Right. You are presented with a highly detailed geographical map of the physical hardware. It feels a lot like playing a real-time strategy game, like SimCity, but for multi-million-dollar IT infrastructure. You're looking at a digital twin of the rack.
And it uses these subtle visual cues to instantly convey critical information to the admin. For example, right next to the visual representation of the NVL72 rack, there's a small, distinct water droplet icon.
I noticed that in the walkthrough. It seems like such a minor aesthetic choice, but when you think about the scale these companies operate at, it's vital.
Right. If an admin is monitoring a dashboard covering a sprawling facility with a mix of older legacy hardware and new AI clusters, they need to know instantly which racks require complex fluid plumbing management and which ones are just traditional air-cooled units that might still be managed in an older module like PodView.
That little water droplet instantly tells them this is a volatile, liquid-cooled asset.
The walkthrough also provided a very honest look at the realities of software development. As Kevin Culp is demonstrating this visual roll-up of the rack, you can see these little yellow warning triangle icons scattered across some of the components.
Yes. I loved this moment because it was just so pragmatic. The software was displaying standard, generic stencil graphics instead of photorealistic 3D models for some of the specific server SKUs.
And Culp directly addresses it. He explains that at the time of this specific software release, they simply didn't have the finalized image assets from the hardware design team.
Typical tech industry pipeline issues.
Exactly. But rather than delaying the launch of a mission-critical management tool just to wait for pretty pictures, they made the pragmatic engineering choice. They shipped the software with standard stencils. It doesn't affect the telemetry, the security, or the management capabilities in the slightest.
It's a great reminder that even when you are building the infrastructure for the most advanced AI on the planet, you're still bound by standard software development constraints. You ship the functional feature today, and you patch the cosmetic graphics in version 3.12.
So true. Now, we've talked about viewing a single rack, but obviously no one buys just one of these. How does SEC handle the massive scale of an AI factory with hundreds of these racks?
It utilizes an overarching organizational concept called pods. While the SEC software discovers and treats a single NVL72 rack as one cohesive organism, it allows administrators to logically group multiple racks together into a pod based on the specific workload they're handling.
The source material used a fantastic real-world example for this. They suggested an administrator might take a dozen of these NVL72 racks and group them together into a pod labeled the ChatGPT Cloud.
Exactly. This allows the DevOps team to abstract the complexity. If the executives want to know the power consumption, the thermal output, or the overall hardware health of their primary language model offering, the admin doesn't have to manually pull reports from 12 different racks and average them out.
They just click on the pod.
Right. The software aggregates the telemetry for the entire workload group, allowing them to apply security policies, perform firmware updates, or monitor efficiency at a massive macro scale.
That macro view is incredibly powerful for executive reporting. But what happens when the red lights start flashing? High-level grouping is great when things are healthy, but when a component actually breaks inside one of those 12 racks, you need to get surgical. How granular does this software allow a technician to get?
That naturally brings us into what the sources refer to as day 0 to day 2 lifecycle management. The software allows you to seamlessly drill down from the macro pod view into the specific rack and click directly into an individual compute tray to see exactly what is happening at a microscopic level.
And this is where the integration of specific hardware APIs becomes critical. The sources talk extensively about SEC harvesting data from Redfish endpoints and using OpenBMC as its source of truth. For the non-engineers listening to this, what exactly are those technologies and why are they harvesting so much data?
Let's demystify those terms a bit. Redfish is simply an industry standard language, an API that allows software to talk to physical data center hardware regardless of who manufactured it. It's like a universal translator for server components.
Okay, got it.
And OpenBMC, which we touched on earlier, is the open source firmware running on those tiny health monitoring computers attached to the motherboards.
So SEC is constantly using the redfish language to interrogate the OpenBMC monitors, asking, how are you feeling? What's your temperature? What hardware do you have plugged in?
Exactly. It polls these endpoints continuously. So when you click on a compute tray in the SEC interface, you aren't just getting a static list. You are flooded with real-time actionable telemetry.
It's all live data.
Yes. You see the exact assigned IP addresses, the specific manufacturer SKU numbers for warranty claims. You can see the health roll-up of the silicon, confirming it has its 2 active CPU sockets and recognizing all 124 gigabytes of memory.
The UI even shows active task indicators, letting you know if an automated script is currently in the middle of deploying an operating system to that specific node.
Furthermore, it leans heavily into user-defined tagging. This is a subtle feature, but it has massive implications for corporate governance.
How so?
Well, if an engineer deploys a highly specialized proprietary AI inference engine to a specific node, they can tag it in the UI. Anyone else logging into the dashboard months later instantly knows the exact state, purpose, and security clearance of that specific piece of hardware within the larger 48U organism.
And they know that without having to run a complicated software audit.
Right, it's right there in the UI.
And from this incredibly detailed, granular screen, the administrator has total remote control. You don't have to leave the control room and walk down onto the freezing, noisy server floor. You can force the server to power off. You can force a hard reset to clear a memory fault. And you can initiate a feature that I think is one of the most practically brilliant, human-centric tools mentioned in this entire deep dive. You can blink the UID.
The unit identification lay. It sounds like such a trivial, basic feature, but its real-world application in a crisis is absolutely profound.
To understand why, you really have to put yourself in the shoes of a data center technician. Imagine it's 3:00 a.m. on a Saturday. You're a tech on the floor of a massive football field-sized data center.
I've been there. It's not fun.
Even though the heavy lifting of the heat removal is done by silent liquid cooling tubes, there's still ambient fans running in the power supplies, massive facility water pumps humming, and industrial air handlers circulating the ambient air. It's incredibly loud, it's disorienting, and you are standing in an aisle staring at 50 identical monolithic black metal racks that all look exactly the same.
And your pager goes off. The SEC dashboard has detected that a single NVMe storage drive has critically failed on a specific compute tray in Rack 42. You need to pull the dead drive and swap in a replacement.
But inside that compute tray, there are multiple identical drives sitting right next to each other. If you reach in, exhausted at 3:00 a.m. and you accidentally pull the wrong drive, let's say you pull the drive that currently houses the operating system running a massive AI training batch, you haven't just failed to fix the problem, you've caused a catastrophic failure.
You've brought the entire node down entirely.
Exactly.
Yeah.
Bad news bears, as Kevin Culp eloquently phrased it in the presentation.
It's the ultimate nightmare for a technician. So, to prevent this, the DevOps admin sitting in the quiet control room simply clicks a button on the SEC interface to blink UID. Down on the chaotic floor, a specific bright blue LED begins flashing wildly right next to the exact failed physical drive.
It brilliantly bridges the gap between the abstract software dashboard and the gritty physical reality of the hardware. It guides the human hand, ensuring that even under pressure, the technician makes the exact right physical intervention.
If we connect this to the bigger picture and expand on this idea of bridging the software and the hardware to prevent human error, another massive leap forward that the sources detail in the lifecycle management section is the concept of firmware bundling.
Yes. This is a monumental quality of life and security upgrade for anyone who has ever had to manage a data center. Historically, updating the fundamental firmware, the foundational code that tells the physical microchips how to operate, was an absolute nightmare of manual labor.
It really was, because a server isn't just one computer, it's a collection of mini computers.
Precisely. You have the BIOS on the main motherboard, the specialized firmware on the network interface cards, the code running on the BMC health monitor, and firmware on the storage controllers.
In older architectures, an administrator would often have to log into each of these subsystems individually, server by server, component by component, and manually flash the updates.
Which is not only incredibly time-consuming, but it introduces the most dangerous variable in IT version mismatch. Let's say a technician spends 40 hours updating 1,000 servers. But on rack number 12, they get distracted and forget to update the firmware on one specific network card. So you have 999 servers running version 1.2 and one server running version 1.1.
In a traditional web hosting environment, that might just mean one server runs a little slower. But in the context of an NVL72 AI supercluster, where these 72 GPUs must function in perfect, millisecond-precise unison to calculate a neural network weight, a version mismatch is fatal.
The system just can't handle it.
Right. That single outdated network card will interpret a data packet differently, cause a microstutter, and potentially corrupt a $10 million AI training run on day 45.
The stakes are simply too high for manual updates. And that is exactly what firmware bundling solves. The SuperCloud Composer software completely abstracts the individual component updates. Instead of flashing servers one by one, the software allows Supermicro to provide a bundled, fully validated package of firmware.
The admin simply tells SEC to apply this bundle to the entire NVL72 compute tray at once.
The software treats the entire the organism as the basic unit of update, not the individual server.
It orchestrates the updates across all the motherboards, network cards, and BMCs simultaneously, ensuring that every single component boots back up on the exact same verified firmware version. It saves hundreds of hours of excruciating manual labor, and more importantly, it completely mathematically eliminates the risk of human-caused version mismatch catastrophes.
Okay, we have covered the brains of this operation, the immense compute density, the NVLink switches, and the deeply granular software required to manage their lifecycle. But earlier in the deep dive, we established that all of this brainpower is utterly useless without the liquid cooling mandate.
Very true.
If the compute trays are the brains, we need to spend some time talking about the heart that pumps the lifeblood through this entire architecture.
We are talking about the unsung hero of the AI revolution, and easily the most fascinating piece of physical engineering in the CDU, or the cooling distribution unit.
As we discussed during the physical layout, Supermicro rigidly places the in-row CDU at the absolute bottom of the rack in rack slot unit 1. But the sources are quick to emphasize that this is not just a generic water pump sitting in a bucket.
Definitely not. It has been painstakingly optimized specifically for the massive fluid dynamics required by the GB200 and NVL72 silicon.
It is a highly sophisticated piece of thermodynamic telemetry equipment. The volume of sensor data that the SuperCloud Composer pulls from the CDU is honestly staggering.
When an admin clicks into the CDU dashboard within SEC, they aren't just looking at a binary pump-on or pump-off indicator. They're reviewing a real-time, highly complex thermodynamic profile of the entire massive rack.
The specific metrics they list in the presentation sound like they belong in a chemical refinery, not a computer lab. The software is continuously monitoring the exact coolant return temperature, meaning how hot the fluid is after it is washed over the blazing GPUs, and comparing it to the coolant supply temperature.
Which is how cold the fluid is when the facility water system pushes it back into the rack. It watches the precise mechanical states and fluid pressures of every single internal pump and manifold valve.
And it measures the overall heat load being generated by the silicon in kilowatts, tracking exactly how much of that heat is actively being dissipated.
But perhaps the most critical metrics it gathers are ambient, the atmospheric dew point, and the ambient humidity inside the data center.
Okay, I have to ask, why does a computer need to know the humidity of the room it's sitting in?
Because when you're piping freezing cold liquid into a room full of electronics, condensation is your absolute worst enemy. Think about taking a freezing cold glass of ice water outside on a hot, humid summer day.
Oh, right. Within seconds, the outside of the glass is dripping with water pulled straight out of the air.
Now imagine those water droplets forming directly onto a motherboard carrying thousands of volts of electricity.
It would instantly short-circuit and destroy the hardware.
Exactly. If the CDU pumps coolant that is too cold relative to the ambient humidity in the room, it hits the dew point and it literally starts raining inside the server rack. The CDU uses all of this massive telemetry to constantly dynamically adjust the fluid flow rate and the coolant temperature.
It's riding a knife's edge to stay perfectly balanced within a safe thermal envelope where the chips stay cool but condensation cannot form.
And if that delicate balance fails, or, if a physical pipe simply cracks, there is an ultimate non-negotiable failsafe. The presenter, Kevin Culp, discusses this at length. It is the external leak sensor mounted on the front of the CDU.
It is arguably the single most critical sensor in the entire multi-million-dollar rack. Culp makes a point to explicitly state that this sensor is configured to represent a hard shutdown condition.
which means it doesn't wait for permission. If that external sensor detects the physical presence of fluid leaking outside of the contained plumbing loops, it does not send a polite alert to the SEC dashboard and wait for a human being to approve an action.
It triggers an immediate emergency hard physical power cut to the entire rack. It violently shuts everything down to save the hardware from catastrophic electrical fires and short-circuiting. It is the ripcord.
And I think it's important to pause here and connect this incredibly dense engineering reality back to you, the listener, because it's very easy to listen to a discussion about dew points, manifold pressures, and external leak sensors and think, this is fascinating, but it has absolutely nothing to do with my life.
But it dictates almost every interaction you have with modern technology. Every single time you open an app on your phone to generate an AI image of a cat in a spacesuit, or you ask a large language model to draft a difficult email to your boss.
Or you utilize an AI coding assistant to debug a script.
Exactly. The speed, quality, and reliability of the response you receive on your screen is entirely physically dependent on these precise fluid metrics staying perfectly balanced in a data center thousands of miles away.
We've spent the last 2 decades being sold the illusion that the internet and the cloud are weightless data. But the AI revolution has proven that the cloud is deeply inherently physical. Data centers are no longer just quiet rooms full of blinking hard drives. They are highly advanced, aggressively monitored industrial plumbing systems.
If the facility water supply experiences a slight hiccup and the coolant return temperature in that CDU spikes by just a few degrees, the SEC software will immediately tell the Nvidia GPUs to throttle their clock speeds to survive the heat. And when they throttle, your AI prompt takes 3 times as long to answer.
Your wait time at your desk is a direct result of the physical plumbing on the other side of the country working overtime to dissipate heat.
It completely reframes how you view the digital tools we take for granted. But what makes this field so relentless is that the hardware industry doesn't sit still long enough to celebrate mastering one architecture.
No, they never do.
As soon as you finally perfect the plumbing and the software for the GB200 platform, the next massive generational leap arrives. And the sources give us a truly fascinating behind-the-scenes look at how software teams manage this relentless hardware transition.
Yes, the presentations spend time discussing the impending arrival of the GB300 architecture. The sources show the SuperCloud Composer software, specifically in its version 3.11 release validation phase, actively trying to adapt to this new GB300 reality.
And what I found most interesting wasn't necessarily what changes with the new generation, but what remains exactly the same.
It is a massive validation of the rigid standardization Supermicro established with the NVL72. Even with the generational leap to the much hotter, much denser GB300 silicon, the overall 48U physical rack configuration remains largely identical.
The philosophical layout, those 5 strict quadrants of management, power, compute, switch, compute, power, CDU, it doesn't change a single inch. The CDU is still anchoring the bottom in rack unit 1. The massive power shelves are in the exact same slots.
So the infrastructure shell remains stable. What changes are the actual compute trays sliding into those slots, now housing the significantly denser GB300 chips and potentially the next generation of NVLink switches required to handle the increased data bandwidth between them.
But this transition period also exposes the gritty, unglamorous reality of enterprise software development constantly playing catch-up with the speed of hardware innovation. In one of the walkthrough videos, as Kevin Culp is clicking through the new GB300 compute tray interface within SEC, he frankly points out bugs that the engineering team is still actively wrestling with.
I loved this moment of transparency. He is showing off the UI, and he highlights a field that is supposed to display the exact GPU model number for the new GB300s, but the field is incomplete.
It just shows the manufacturer name Nvidia and some basic base-level specs, but the highly specific model string is totally missing from the database pull.
And he doesn't try to hide it or spin it. He just casually remarks, "We'll get the engineering team to fix that before release."
It is a very raw, honest look at the iterative, messy nature of building these management tools. The hardware teams are moving at light speed, and the software teams are essentially trying to build the airplane while it is already taxiing down the runway at 200 miles an hour.
He also mentions another software catch-up issue regarding the firmware bundling we praised earlier. He notes that while they have the bundling feature working perfectly for the Nvidia components on the new GB300 trays, the development team is still actively writing the code to bundle the super micro-specific BIOS and BMC updates.
They were aiming to have it finished by the end of the year, right?
Right. It shows that achieving that unified, pristine, single pane of glass management experience is a constant, grinding battle against the pace of physical innovation.
Okay, I think it's important we shift our perspective here. We have spent an hour diving deep into the microscopic realities of the NVL72 and the impending GB300. We were talking about massive 48 rack unit monoliths that require industrial liquid cooling lines, dedicated out-of-band networks, and multi-million-dollar capital investments.
Right. We've basically been describing the infrastructure of a trillion-dollar tech giant.
Exactly. But what if you aren't a trillion-dollar tech giant? What if you are a smaller player? Because if this massive multi-million-dollar, multi-month installation is the only way to run AI, then you are essentially locking startups out of the AI race entirely.
Which would be disastrous for innovation.
How does a hardware industry prevent an oligopoly where only 3 massive companies can afford to play the game?
This is a vital question for the health of the entire tech ecosystem, because even if a well-funded startup has the capital to buy an NVL72 rack, the sources explicitly acknowledge that the supply chain for these top-tier components is incredibly constrained.
The lead time to actually get a 48U liquid-cooled supercluster delivered, plumbed, and installed can be several grueling months.
And a startup simply cannot afford to wait 6 months to begin training their models.
So how do you get skin in the game immediately? How do you start an AI factory without having to buy the entire factory on day one? That brings us to what the sources introduce as the NeoCloud on-ramp, the GB200 NVL4 platform.
Specifically, they detail the model ARS-121G MB2B LLC. And this platform represents a completely different philosophy of scale. Instead of a towering 48U monolith, the NVL4 is a 1U server.
A single rack unit. It's roughly the size and shape of a large, heavy pizza box.
But the critical detail is that it is still entirely liquid-cooled. It doesn't compromise on the fundamental physics mandate we discussed at the top of the show. It is designed as a highly accessible, much smaller initial investment for what they call NeoCloud data center operators.
Essentially, hungry startups or mid-sized enterprises that want to begin building high-performance compute clusters without mortgaging their entire future on a single 48U rack.
It allows a company to start with 1 or 2 of these 1U servers, rack them in a standard colocation facility that has basic liquid loop support, and immediately begin building momentum and generating revenue.
And just because it's squeezed into a 1U pizza box chassis doesn't mean it lacks firepower. The specs they cram under the hood of this thing are deeply impressive for its physical footprint. Let's pop the hood on this.
Let's do it.
This single 1U box contains 2 72-core Grace ARM processors.
Which, just to put that in perspective, means you have 144 independent CPU cores dedicated solely to managing traffic and feeding data to the accelerators.
Right. And to handle the immense amount of training data those cores require, the unit features extensive NVMe local storage capabilities. The sources note it includes hardware RAID support, ranging from RAID 0 all the way to RAID 60, managed by high-end Marvell or LSI controllers.
Let's unpack why a startup cares about RAID 60 specifically. When you are feeding data into an AI model, the speed at which the hard drives can read the data is a massive bottleneck.
Right. The GPUs are just waiting for the data to arrive.
Exactly. RAID, which stands for Redundant Array of Independent Disks, allows you to group multiple hard drives together. RAID 0 stripes the data across multiple drives, making read speeds incredibly fast. But if one drive fails, you lose everything.
High risk, high reward.
But RAID 60 combines that blistering striping speed with dual parity redundancy, meaning an AI startup can read their training data at maximum speed. But if 2 separate hard drives physically break during a heavy training run, they don't lose their data and they don't have to start over. It provides enterprise-level reliability in a 1U form factor.
And the main event inside this box, alongside the 144 CPU cores and the redundant NVMe storage, it houses 4 GB200 GPUs.
4 massive 186 gigabyte AI accelerators squeezed into a 1U space. The compute density is just wild.
But what is really fascinating to me isn't just the physical hardware, it is how the SuperCloud Composer software treats this smaller unit. SEC doesn't treat the NVL4 like a toy. It offers some incredibly powerful enterprise-grade features for data mining and compliance that are absolutely crucial for a startup trying to ruthlessly optimize their limited operations.
There are two specific SEC features highlighted for the NVL4 that really stand out for smaller operators. The first is the deep metadata export capability. The SEC software allows an administrator to dump absolutely all the component data, telemetry, and health metrics into standard, highly portable formats like CSV, JSON, or what they call a YAML tarball.
For the non-developers listening to us, what is a YAML tarball, and why is this export feature so important for a NeoCloud operator?
A YAML tarball is essentially a neatly compressed digital zip folder full of highly structured text files that contain configuration data. The reason this matters is that a scrappy startup NeoCloud operator needs to be hyper-efficient, but they likely do not have the budget to purchase massive, proprietary, expensive data analytics engines to monitor their hardware.
Right, they can't afford a massive Splunk or Datadog contract yet.
Exactly. By allowing them to natively export this incredibly rich telemetry metadata directly into standard JSON or CSV formats, SEC democratizes the analytics. A startup engineer can ingest that CSV file into standard pivot tables or feed it into their own homegrown Python scripts to perform deep data mining.
That's huge for capacity planning.
It is. Critically, it allows them to perform accurate capacity forecast planning. They can track exactly how their thermal heat load and electrical power draw correlates with their specific AI workloads over a month.
And that data allows them to predict, with mathematical certainty, exactly when they will run out of compute power and exactly when they need to order their next NVL4 server.
It allows them to scale smartly, rather than just guessing. And the second critical software feature highlighted for the NVL4 is all about strict security and compliance, specifically regarding the FRU and the DMI.
This is a deeply technical but vital security mechanism. FRU stands for Field Replaceable Unit Data, and DMI is the Desktop Management Interface. Essentially, this is the digital fingerprint of the hardware.
It's the hard-coded information that identifies exactly what the motherboard is, what the serial numbers are, and how it presents itself to the broader network.
The SEC software allows administrators with the right permissions to edit this FRU or DMI information. However, the software enforces incredibly strict governance over when you can make those edits.
Right. The presenter specifically notes that you can only edit this foundational identification information unless an operating system has already been deployed to the node, or unless the hardware's health rollup is currently showing a critical failure state.
And those two unless conditions are doing a massive amount of heavy lifting for system stability. Why does this software lock you out of editing the serial numbers if an OS is running?
Because changing the fundamental hardware identification data while a system is actively running workloads is like trying to change a car's VIN number and license plate while it is driving down the highway at 80 miles an hour.
That sounds dangerous.
It requires a deep physical reboot for the network to recognize the new identity. If the software allowed an admin to change the DMI while an operating system was actively processing an AI workload, it would cause a catastrophic system panic and instantly corrupt the environment.
And if the machine is actively failing, if it's in a critical state, the software locks it down so a technician can't accidentally mask the hardware failure by overwriting the error logs with the new hardware profile.
By mathematically enforcing these checks and balances directly within the SEC user interface, it physically prevents a tired or junior admin from making a seemingly harmless configuration change that accidentally crashes a vital revenue-generating client workload.
It enforces discipline in an environment where startups can't afford a single mistake.
And finally, the true brilliance of the NVL4 is how it fits into the broader software ecosystem. Even though this NVL4 is just a single 1U pizza box chassis, the SEC software maps it into the exact same overarching logical tree architecture as the giant 48U NVL72 monoliths. It scales perfectly.
Walk me through that logical scaling.
Within SEC, the logic starts at the chassis level, in this case, the 1U NVL4 box itself. Then, as you add more boxes, the software logically maps them up to a drawer layer and then up to a rack layer.
And just like we discussed with the big racks, an admin can take multiple racks of NVL4s and group them into a pod to manage a specific workload group.
And all of those pods roll up to the overarching data center layer. It provides a completely seamless growth path for the business. A NeoCloud startup can literally begin their business with 2 1U servers in a rented closet, manage them cleanly using SuperCloud Composer, and as their business explodes over the next 3 years, they can eventually grow into managing dozens of pods filled with massive NVL72 superclusters.
All without ever having to change their management software, retrain their DevOps staff, or alter their fundamental operational logic. The software scales from the pizza box to the skyscraper seamlessly.
It is a remarkable piece of forward-thinking engineering.
We have covered a truly massive amount of ground today, pulling from some incredibly dense, deeply technical sources. We started by looking at a literal crisis of physics, the stark reality that our power grids are failing, mandating a total industry shift to liquid cooling, because traditional air simply cannot dissipate the nuclear-level thermal density of modern AI chips.
From there, we explored how that physical constraint mandated a completely new approach to hardware architecture. We broke down the incredibly rigid, non-negotiable five-quadrant layout of the 48U NVL72 rack and discussed the philosophical leap of treating that massive structure not as a collection of parts, but as a single holistic organism.
We dove deep into the SuperCloud Composer software UI, exploring how humans actually manage this beast, from grouping assets into pods for a macro view, to the incredibly practical genius of blinking a UID light to guide a tired technician on a noisy floor.
And we covered how it prevents million-dollar catastrophes through automated firmware bundling.
Right. We shined a light on the unsung hero of the revolution, the cooling distribution unit, unpacking the staggering volume of thermodynamic telemetry it gathers to prevent condensation, and its ruthless ability to pull the ripcord and cut power if a leak is detected.
We also looked at how the industry is already sprinting toward the GB200 while software teams wrestle with bugs and missing strings to catch up.
And finally, we looked at how smaller players can actually enter this game. We explored the 1U NVL4 NeoCloud platform, detailing how startups can leverage advanced metadata exports like YAML tarbles to ruthlessly optimize their operations, while relying on hard-coded software lockouts to prevent catastrophic human errors.
The absolute through line of this entire deep dive is that the cloud is an illusion.
Every single time you interact with AI, this invisible, heavy, intensely monitored liquid-cooled infrastructure is working furiously in the physical world to make it happen. The constraints of our digital future are entirely physical.
And as we wrap up, this raises an incredibly provocative final question for us to ponder. We spent an enormous amount of time today discussing the absolute richness of the telemetry being gathered by SuperCloud Composer. We talked about redfish endpoints pulling thousands of data points a second on heat load, fluid manifold pressure, ambient dew points, and component health.
It is a literal ocean of thermodynamic data.
Exactly. But right now, today, all of that data is simply being surfaced to a human DevOps administrator sitting in a control room asking the human to make a decision about throttling or maintenance.
Right.
But if we connect this telemetry to the broader, unstoppable trajectory of artificial intelligence, how long until the AI models themselves are given direct access to their own redfish endpoint telemetry?
Oh, wow. That is a wild thought.
Think about the implications. What happens when the AI is no longer just a blind mathematical workload running on the silicon, but becomes actively, continuously aware of its own physical constraints in real time?
It could monitor itself.
How long until an AI model realizes it is getting too hot and dynamically self-throttles its own training parameters based on a slight 1-degree fluctuation in the coolant return temperature to ensure it doesn't crash?
Or, to take it even further, how long until the AI itself is tasked with analyzing that ocean of telemetry to begin redesigning its own physical liquid cooling infrastructure?
Generating new, hyper-optimized plumbing blueprints to squeeze out one more degree of thermodynamic efficiency that human engineers just couldn't see.
The organism becoming actively aware of its own circulatory system and then choosing to evolve it. That is a staggering thought to end on. It brings us right back to the tension we started with. We constantly want the world of AI to be pristine, to be entirely contained in the clean realm of software and abstract code.
But the reality is undeniably aggressively physical.
It is murky. It is blisteringly hot. It requires intense industrial plumbing, and it demands constant, flawless telemetry just to survive. The digital future isn't floating in the sky. It is a massive, liquid-cooled organism anchored to the floor, and it is evolving faster than we can build the tools to manage it. Something to think about the next time you casually type a prompt into your phone. Thanks for joining us on this deep dive.